Okay, and last but not least, we're going to talk about metamorphic rocks. So I know the other videos were kind of long in the PowerPoint, so this one will be a little shorter. Let's hope that that's true. Metamorphic rocks, there isn't as many samples for us to look at, and we're going to really kind of get down to just the basic information that you need for metamorphic rocks. So let's take a look at what we got going on here. So the reason that metamorphic rocks are important to us is, like all the other rocks, they tell us something about the history of what occurred here. So we want to be able to understand what has happened in the past geologically, and the rocks can tell us that story. We like that as geologists, but also, of course, for us, sometimes we want to look at the stability of some of these rocks. And undergoing metamorphism, some of these rocks can become extremely strong and durable, which would be good for stability. Others might develop a weakness that could be a problem, and so we want to be aware of those differences. So look, when we talk about metamorphism, what we're saying is we're taking a pre-existing rock, and that can be any pre-existing rock. As long as it exists as a rock, we can alter it, change it from what it was to something else, and we're doing that through a combination of pressure, temperature, and fluids. And so we're taking an original rock, and the example you see here is a shale or a mudstone. The original rock before it was metamorphosed is called the protolith. That's what this term means here. So take this rock and the protolith, we're going to alter it. We're going to squish it, we're going to heat it, we're going to add a little fluids there, mostly some waters, and we're going to change it into something else. In this case, it looks fairly similar, but it has some different properties. And so the slate would be a metamorphic term, and we would argue that the protolith for the slate was this shale. So what was it before we turned it into a metamorphic rock? It was a shale. And so remember, I can do anything. I could take a granite and I could metamorphose it, turn it into something else. I could take a basalt. I could take a sandstone. I can take a limestone. I can even take a pre-existing metamorphic rock and increase or change its metamorphism, change it into something else. Okay, so that's what metamorphism does for us. So all of this is happening in the solid state, which means we're not melting the rocks, because remember, if we melt them, then they cool and crystallize. By definition, they become igneous. So here we're just altering them. You know, it's usually at some place where it's hot enough. There's some fluids that can move in there that can facilitate some crystal growth and change, and the pressures, and these are all causing the rocks to slightly change, and then they're becoming something new with some new properties. So they're technically a new rock. We give them a new name. The three main factors here, the causes, things that are making our rocks change, are heat, differential pressure, and fluids. And almost every type of metamorphism, all these come into play, some more dominant than others. And so when we look at metamorphic rocks, at least at the very basic level, we're looking for a texture. And the textural terms we're going to use for metamorphic rocks are what's called non-foliated and foliated. And so really we're looking for this texture where the minerals are kind of aligned, giving them a layered look. And so that would be what we're going to call foliated. So if we're like, all right, so what is foliated? Well, we're going to argue that this foliated texture here is the result of extreme differential pressures that are applied to the rock. And so when we see this type of texture, what I want you to think is high differential pressure, and I want you to think in this term, regional metamorphism. Because in order to get differential pressure, which means the pressure is not equal on all sides, we need a force like a convergent plate boundary. Now there could be subduction or not, because we could have continents, but that huge stress where the two plates collide, the stress in that direction if they're colliding into each other is greater in that horizontal direction than it is in any other direction. So it's not the same all around, it's differential. It's got this high pressure in that horizontal direction. And what that does is going to give the rock a texture. And that texture, like I said, is called foliated, and it has to do with the minerals that are in the rock actually realign themselves, and they form what looks like some layering. But it's not like sedimentary rock layering where it's depositional. This is a creation from this high differential pressure. Now look, there's some temperatures involved here, and there's fluids involved here too, and regional metamorphism, and we call it regional because it typically involves a large area of rock, and it does involve higher temperatures and fluids, but the big driver that's causing the texture here is this high differential pressure, as opposed to what we're going to refer to as contact metamorphism, where there is not a texture like that, so we'll just call it non-foliated. So there's no aligning of crystals, no layering that you can visually see. The big driver here is the temperature. And so this is usually occurring where we have molten rock. We know it forms at depth, and it moves upward to the surface. And so this molten rock is incorporating other rock into the melt as it moves. But at some point it kind of stops and emplaces itself, and it can't move anymore, but it's still a liquid, but it heats the surrounding rock, and that is the driver that's alternating this zone around a magma chamber into something else. And so the big driver here is the high temperature, not the pressure. So we're not getting the alignment of minerals, we're not getting that foliated texture, just getting a difference in crystal size typically. And so this high temperature is the driver in contact. It's usually just around, or a zone around a magma chamber is the most common way we get contact metamorphism. And the argument is coming into contact with something that's really hot, as opposed to regional, which is larger areas and usually related to convergent plate boundaries and this foliated texture. Alright, so what is foliated texture, for crying outside? Alright, here it is. This is what foliated texture, and this is the differential pressure story. So you can see that the stress is greatest in this horizontal direction in this diagram. The argument is you have an original rock where there are crystals that are elongated. So they're not perfect squares or circles. They have a long axis and a short axis. So kind of like these little rectangles here. And with enough stress and some heat and some fluids, we can slowly start to align these elongated crystals perpendicular to the greatest stress. So they start to line up, and they start to form this layered look. Now this rock below here is a very high grade metamorphic rock, but it shows the foliated texture the best. This is actually called a gneiss. And so these are alignment of minerals, right, caused by this differential stress. This is the texture you're looking for in a metamorphic rock. Some type of, I know the term is not correct, looks like layering, but it's not caused by deposition, remember. It's caused by this stress, this collision, usually at a convergent boundary. So we argue that the foliated texture means regional metamorphism, probably near a convergent plate boundary, and it's the result of this high differential pressure. Even though temperature is involved and fluids are involved, it's the big differential pressure that's causing this texture here. And that's some of the interpretation that we would give for a foliated metamorphic rock, is a convergent boundary of some kind. So it's not this confining pressure, which means pressure from all sides. We wouldn't get any alignment. So it's not just if we can kind of slowly, put it down in the ground a little bit. We need that differential pressure to create that foliated texture. And so here's a good example, I think, of the different types. So we're going to argue that there's two main types. Now, there are a variety of types if we get into the gory details. We don't need that for this class. Regional, this high differential pressure zone, and contact. And so this diagram on the right is a great example. So here is where I would see some contact metamorphic rocks, where the heat is the driver of change here. And it would just be in this little zone around this magma chamber that is cooling and solidifying. As opposed to my foliated rocks, which are here because there's a collision somewhere. I'm building some mountains because I'm slamming these rocks together in some type of convergent plate boundary. When I'm near the surface and there's not enough heat or fluids to cause metamorphism, I can bend and fold the rocks. But as I get deep enough and there's some heat and fluids applied, I can start to change the rocks, metamorphose those. And the foliated rocks that we really care about are the four that are kind of listed here that I'll show you. It's the slate, the phyllite, a schist, and a gneiss. And the argument is that they're more metamorphosed as we go down here, a higher grade. And so they've undergone more heat and probably a little more differential pressure. And so the foliated texture is much more pronounced, and probably the crystal sizes of the minerals are a little larger, easier to see. And so that's really the basics of our metamorphism. Two types, although in reality there's lots of types: contact and regional, and the reasons for what we just kind of discussed there, right? So other sources of heat we can get. We talked about magmas being the main source for our contact metamorphism for heat. You can bury some rocks and get some heat, and that can alter them slightly, and you can get some heat from subduction going on, right, because it's causing some melting to occur there. Fluids. Where are all these fluids coming from? Well, we know that in subduction zones, fluids are leaving the minerals that are being dehydrated as they're pushed down into the mantle here. We get some fluids from some magma chambers as they crystallize. And we get some fluids from when we bury rocks and squish them. We get some fluids out that way. So there's plenty of fluids available to help with our metamorphism event here, but this is why a convergent plate boundary is useful for the change, because it's providing all the things we need to change our rocks. And so just like all the other rock types, we would use a chart to help us figure out what type of metamorphic rock we have. And like all the other rocks, there's some method to the madness. In this one, it is looking for a texture, specifically what we're calling foliated, where it looks like it's been layered. And the four rocks that we care about that are foliated are these four here. And so a slate is not much change happening to it. It looks very similar potentially to a mudstone, but it has been changed. A phyllite, a little more changed. The foliated texture is a little easier to see. The crystals are a little bigger. A schist, the foliated texture is very pronounced, and we see crystals that are fairly large. And the gneiss was that banded light and dark mineral that I showed, rock that I showed you earlier, where we really see this pronounced foliated texture. We would argue all of these are from some type of collision, probably from a convergent plate boundary, because they all show that foliated texture. The difficulty is sometimes differentiating between these, because it's hard to see sometimes the changes because they can be subtle. And what they used to be, mudstone is the popular version. There's a lot of mudstones around, and they have those elongated minerals that lend themselves to this foliated texture. And the other types are here, but for our class, we really just care about these two here, a quartzite and a marble. These are from whether you cook. A quartz aragonite in our story is just a sandstone. When you cook a quartz sandstone, you can get a quartzite. When you cook a limestone, you get a marble. And so we'd argue that these two are from contact metamorphism because no foliation there. They've been altered by this high heat environment. So the non-foliated texture would indicate a contact metamorphism event. Now look, in reality, there's a bunch of nuances here. There's, some variability, and there's exceptions and all that kind of stuff. We don't need that depth here when we're talking about intro geology class, and we certainly don't need those specifics for our hazards that we want to look at. So I think that explanation is enough for what we need. And so just a few other imagery that may or may not help. You can see this is the metamorphic zone here that I have based on the heat that's being produced by this granite pluton as it cools. So we get different degrees but all these would be non-foliated because high heat is the driver there. we talked about regional covering large areas, and it's because some type of convergent boundary event is causing that. These are the rocks that we would get from our foliated regional event here. And, you know, just another example of how you can take let's say this is a sedimentary rock that's layered flat, and crush it. You can actually bend it, but you'd actually also align the minerals in this brown layer here, and they would become foliated. So you'd have these foliated rocks here that are layered vertically, and then this folded. It can get crazy, and in the field it can be very difficult to see. So anyway, that's our regional. Go off on a tangent there. Non-foliated, we only care about, remember, quartzite and marble are the only two we really care about. And then the foliated rocks, these are the four we want to kind of look at. And the typical protoliths we talked about, shale, sandstones, and potentially some granites. And these are our non-foliated ones. So just a quick look at some of the samples that you would see potentially in lab. We have a quartzite and a marble. Though the colors here are different, the textures are very similar. These would be non-foliated, no layering here. They were cooked, so contact metamorphism. And when you have a non-foliated metamorphic rock, one of the ways that you can identify what you have is by performing a test similar to our sedimentary chemical rocks. Because the quartzite is made of quartz sandstone, quartz is extremely hard. I should take my steel nail and try to scratch it. If I can't scratch my quartz, the rock, it's a quartzite. The marble, on the other hand, I could scratch, but marble is made of limestone. Limestone is the protolith of marble. And what happened there? It got baked. But what's limestone? It's calcite, which reacts to my hydrochloric acid. So if we were in the lab and I plopped these two down next to you, and I said which is marble, which is quartzite, you could take a little drop of hydrochloric acid, put it on each. The one that fizzed is the marble, the one that doesn't is the quartzite. Voila, you're done. For our foliated rocks, we have our slate, which we can see some layering in here. This is our foliation, but the crystal size is pretty small. We get a phyllite. The shininess you see here is the increase in size of our minerals, and so we have a little coarser minerals. Still some layering we can see. And we get this crazy schist, which is super shiny, bigger crystals. Once again, you're looking for the layering and the foliation. And then our gneiss, which is the high grade one, really easy to pick out typically, that foliated texture there. And then lastly, we'll talk about, we said the protoliths, right? What's the protolith? Sometimes we can tell, sometimes we can't. And so what we can do for some of those things is we use what's called an index mineral. So every once in a while when a rock gets metamorphosed, there's specific minerals that form under the conditions that that rock was under. And so we can use those particular index minerals to tell us what this rock underwent in relation to temperatures and pressures, because certain minerals only form under specific temperatures and pressures. And if I have it, I'm like, oh, this rock must have been buried this deep under this pressure, and then that can help me determine if it's a collision between kind of plates and kind of what depth it forms there. So additional information can be gained about the metamorphic event from specific minerals that form in our metamorphic rocks. And then we talked a little bit about this already, that our quartzite protolith is a sandstone and our marble protolith is a limestone. For our other foliated rocks, typically the mudstone is the most common for slates, schists, phyllites, and even for our gneisses we can have mudstones. And in addition, granite is a protolith for the gneiss. And then once again, here's our lovely chart that we can use to name the rocks. This is something you'll look at when you do the lab. And voila, I think we finally made it through all the rocks. And so we've kind of gone through all of this rock cycle here. Igneous, sedimentary, minerals, metamorphic rocks. You should have enough information to move on, and then we can talk about all the crazy hazards that geology brings to us. Okay.